my name is Alex, and today I'll try to make a deep dive into EIP-8141 frame transactions. So let's start from defining the problems that we are trying to solve. In, say, Bitcoin in its simplest form, a transaction performs the validation of a signature, transfer of BTC tokens from one address to another, and it also pays its transaction fee. So Ethereum comes along and it introduces, in place of BTC transfer, arbitrary code execution. However, the validity of transactions still defined by signature validation and gas fee payment that is rigidly defined by the Ethereum protocol. So users must rely on their private key controlled accounts or externally owned accounts to include transactions in Ethereum blocks. So someone may ask what is wrong with using EOAs. So there's a number of things. First, EOAs just have a completely unforgiving user experience. So we tell to people we have reinvented the future of finance, so please write down these 12 words on a piece of paper and hide it around your house. And you cannot change this logic. The logic that is given to you by the protocol is there. Your private key has a super admin control of your account, and there is nothing you can do to modify it, put any kind of limits. You also need to pay your own gas fees. And that is becoming an issue for users who are onboarding on Ethereum, and especially in the multi-chain environment, where people are often missing native tokens for their specific chain. And last but not least is that the cryptography used by EOAs today, it's all same, and in case if it were to be to fail, it would mean a total collapse of the Ethereum chain. And as has been in the news recently, Google published a research claiming that by year 2029, the entire cryptography used in Ethereum today may become obsolete due to progress with quantum computing. So the process of replacing this protocol-defined logic with a programmable validation of transactions is what we call account abstraction. The first viable attempt at account abstraction on Ethereum was taken by ERC 4337. What it allowed users to do is they could adopt smart contract accounts as their on-chain identity and find a designated, sophisticated service providers, third parties who would control EOAs for the inclusion of transactions in a block. So they would submit assigned messages that we call user operations to this entity called bundler, and the bundler will actually put the transactions on-chain. The first step towards native account abstraction was taken later by EIP-7702, which allowed externally owned accounts to inject code into their address by signing a special verification authorization message. So it fully addressed the problem of EOAs not having execution code, but it didn't do anything with validation. You still have the private key that has full control of your account that you cannot rotate. With that in mind, we are seeing a growing adoption of account abstraction solutions across all EVM chains, and they're often used together. There has been more than 1 billion of user operations signed across all the chains, and more than millions of 7702 authorizations. That doesn't mean the account abstraction was solved by these projects, because there are a number of issues. The first family of issues is the privacy, censorship, and centralization. There is around a dozen of bundler providers on the market. However, a smaller number controls the vast majority of this service, creating a kind of bottleneck. And the other one is complexity, not only gas overhead, but also the entire technology that has to be built in an out-of-protocol solution. And with 7702, the problems are various, but there is also an issue of abuse of this protocol, where you can see almost 70% of transactions with 7702 were classified by some block explorers as a crime. The idea of introducing native account abstraction on Ethereum is absolutely not new. It's the opposite of that. In fact, it's one of the earliest EAPs. The first one had a number of EIP-86. And for years since, there has been a significant evolution of the way we think about account abstraction and what we need to do to fully solve it on-chain. And this accumulated knowledge allowed native AA to become a huge topic for the upcoming hard fork called Hegota. So for Hegota, multiple client teams and alternative layer ones introduced the proposals specifying their preferred way of addressing native account abstraction. And I am bringing those proposals up because they kind of allowed us to define the design space of native account abstraction solutions on Ethereum. So for a number of decisions, you have to put yourself on a point between like two extremes on the axis of this design space. So for example, you can have a fully arbitrary validation logic in your accounts, or you can enshrine some specific validation operations or some subset of operations. You can allow completely arbitrary access to storage of the Ethereum state, or you can limit what storage can be read. In more general terms, you can try to foresee and accommodate future needs for account abstraction, or you can try to make a short list of like particular pain points that you are trying to address and like check them out one by one. And like emotionally, you can be like kind of brave now, or you can try to delay making like certain core decisions as much as possible. When I say brave, I'm saying like specific fears people have about the future. Like sometimes they would say that maybe somebody in the future will come up with an even better native account proposal. So now is not a good time to adopt native account abstraction. And sometimes there are just legitimate concerns about the complexity of any account abstraction approach, or discussions about the specifics or timelines for post-quantum upgrades. Here we introduce EIP-8141. This is a frame transaction format that tries to make all the right choices and more ambitious decisions in a design space in order to become like an endgame account abstraction proposal, meaning it contains a modular transaction structure with fully programmable transaction validity, full access to Ethereum state. It separates between gas and execution approvals. It has native support for Passkeys, it has native support for atomic batching, and crucially, it also supports backward compatibility with existing EOAs, which means users don't need to migrate to smart accounts to start benefiting from this transaction type. So now we begin the deep dive. Let's begin from the name. What do we mean by frame transaction? So legacy transactions on Ethereum have a single top-level execution frame, meaning you create a transaction from your EOA to a specific target contract. And this target contract can make inner calls, and these calls will be inner execution frames of this transaction. But there is always one top-level frame. This changes with frame transactions. So a transaction now contains multiple top-level frames, and each of these frames has a modifier, and the modifier specifies for the Ethereum protocol the role this frame has in the transaction. And the crucial role is a verify role. Verify role signals to the Ethereum that if this frame is to be reverted, this transaction is not inclusible in a block. So it's not the transaction that is included in a block and reverted. It's a transaction that cannot be in a valid block. It is usually followed by execution block frames, and you can join execution frames into an atomic batch that can either execute or revert in its entirety. In terms of transaction payload, like all existing legacy transaction types specify their target contract, message data, value, and gas limits. So we extract these parameters, and we put them in a nested array of frames, meaning you still have this shared data of like sender, nonce, and your gas parameters, but then you'd specify an array of calls the transaction is making. Let's look into the modes that you have, the modifiers of the frame. The first one I already started talking about. It's a verify frame. And the verify frame has to end with an execution of a new opcode we call approve, because we want to prevent existing contract from like accidentally accepting frame transactions. So the contract needs to explicitly opt into a role that it is taken in the frame transaction. And the verify frame is static, meaning it can read all the Ethereum state, but it cannot write into it. The default is a regular call from an entry point, which is just a constant to your smart contract. And sender is an interesting frame where you can call directly to a target, in a way circumventing your smart account. The approve opcode, there are two operations, of course, you may need to approve for a transaction, the execution of it and the payment of its gas. And there are two separate operations, and you can issue both of these approvals within a single frame if your smart account is paying its own gas. So let's zoom into a sequence diagram. So for example, this is a transaction that uses a gas abstraction. So it uses a gas payer contract, which will be invoked in the verify frame, and this contract will issue an approval for payment, and a smart account issues an approval for execution. These two frames is what we call a validation prefix of the frame transaction. This is the entirety of code that you need to run to figure out if the transaction is includable on-chain. Previously, that was defined by the protocol, the ECDSA verification and the nonce check and the balance check. This is followed by the execution normally, and this is where you can see the difference. The default call makes a call to your smart account, and the smart account interprets the data you are sending to it. It can make nested, like inner calls based on the data you gave it, and the sender call goes directly to the target contract. So your smart account approved this call, and it is just executing this call, and it can have the inner calls, whatever shape. Now, legacy transaction types have opcodes to expose the inputs of these transactions into the EVM, like message, value, data, origin, and stuff like that. This is, of course, not applicable for frame transactions because there is an array of these things. So we have to introduce 4 opcodes in order to expose the entire structure of the frame transaction into the EVM. And there is no hiding here. All of it, except for the signature, is available throughout the entire transaction body. Now the interesting aspects. In order to support existing EOAs that have no code injected into them, just like you sign a transaction, frame transaction with your EOA, that means that you will be provided a code for you. This is a default canonical EOA code that will run in your validation frame, and it supports both EC recover and P256 signatures for passkey support. And another canonical feature is a canonical paymaster for gas abstraction, meaning that this is not provisioned for you. This is a code hash that we allow you to use if you want to propagate your transaction through the peer-to-peer mempool of Ethereum, because if you were to use an arbitrary paymaster, you could have issues with a single paymaster suddenly refusing to pay gas for multiple entities, which is bringing us to a question of trade-offs that you need to do when you're making ambitious choices. So we made ambitious choices of allowing arbitrary validation logic. So of course there is a flip side of that. Now in a mempool, when you receive a transaction, you need to execute some code in order to know if this transaction is even valid. And we allowed arbitrary storage access, so that means that you now need to keep all the state and look it up while running this code, so you can decide if the transaction is valid. So, and the way we were brave means that if a single state change happened before you're executing, like it may invalidate the entirety of your mempool. So in a perfect world, you would like every transaction to live in its sandbox, so you can validate all of them in parallel. If you find one that is invalid, you just throw it away and you continue with the valid ones. And the worst thing that can happen to you if they are not sandboxed and one state change happens on chain, and now the entirety of your mempool is invalidated because they all depended on the same slot. This is what we call a mass mempool invalidation attack, and it's a significant like DOS vector. So how do we deal with this? We introduced what we call a mempool validation strategy, which is a way to decide which transaction can or cannot pass through the peer-to-peer mempool. The limitations are applied on the level of storage. You will only allow reading the inner sender storage in validation code. We only limit the access to opcode that are not providing environment introspection. You cannot see like block number or stuff like that. And we cap the verification gas at around 100,000 units. And if you're using a paymaster, it has to be the canonical one. But the thing is important to note that this is applied by the mempool nodes. It is not a limitation on the transaction type itself. If a transaction is included by a block in a private submission pool, that is still valid, and we expect alternative mempools to exist. Now about the timeline and inclusion of this EIP. So the EIP-8141 is currently considered for inclusion not in the next fork, not in Glamsterdam, but in the following one called Hegota, which I assume is going to land in around 2027. And of course, being like considered for inclusion, it means that there are multiple steps that this EIP still has to go through before it can be considered like included. Of course, a proposal of such scale and with these implications cannot simply exist without becoming a hotly discussed and debated topic across the Ethereum, like crypto Twitter and Ethereum community. And I believe this is a beautiful thing about Ethereum, how decisions are actually often made by the community. And I want to address the specific feedback that we sometimes receive that frame transactions are complex. So in my opinion, like every feature that we have in a frame transaction exists to address a strategic use case for Ethereum. And if you look at some like ways to simplify native account abstraction, it seems like you risk to snowballing even more complexity into Ethereum over a longer period of time. So what do I mean by that? How can we minimize complexity in Ethereum by introducing a new transaction type and a complex one? So the idea is that we introduce some, but we will be able to limit or even like exclude some complexity in the future, which will make it worth it in the long run. So first issue that we kind of starting to see is multiple chains are starting to introduce their own take on account abstraction. And these are major chains, so all the tooling, all the ecosystem will have to support them, and we will end up with a compatibility matrix of what transactions exist on each chain. Another issue is, of course, we cannot run away from quantum computing progress, and at some point in the future, we will need to design a post-quantum transaction type. And that can be an issue if we have to introduce like a special EOA that is a post-quantum signature. And frame transaction provide a very like agile and extensible transaction type. You could design ways to implement post-quantum signatures. You can implement signature aggregation. You can implement post-transaction assertions or MEV protections on top of an existing transaction frame. In case we were to migrate to some zero-knowledge-based virtual machine or anything, the design translates perfectly to that. So in summary, we can avoid adding more transaction types. It can become an endgame transaction time. We can avoid introducing new EOAs. After that, we can avoid keeping the existing EOAs post-quantum, and we can remove the code and all transaction types. And eventually, we can supersede the entirety of ERC-437 stack, making like a number of things obsolete. OK, that's it. Thank you very much, and thank you to the co-authors of this EIP. I will take the questions.